Hello. Good morning. So, we are going to look at this paper Quantum Inspired Embeddings Projection and Similarity Metrics for Representation Learning. This paper, the authors of this paper, they're all from Germany, German Research Center for Artificial Intelligence and Department of Physics, RPTU Kaiserslautern, Landau Kaiserslautern, Germany. So we are gonna look at this paper. We will use some tools such as Mistral and etc. So let's go. So this paper introduces a novel approach to embedding compression and similarity measurement in the context of representation learning, particularly focusing on NLP tasks. So the key contributions, obviously, number one, quantum inspired projection head. So the head that maps classical embeddings onto quantum states in Hilbert space. So that helps us to leverage those qubits, quantum bits. This approach leverages quantum circuit-based operations to reduce the dimensionality of embeddings while preserving similarity relationships between vectors. And it is also designed to be efficient and scalable with classical computing environments, distinguishing it from more complex quantum machine learning algorithms. Alright, and also the similarity metric, they have a quantum inspired similarity metric. So the name for this is fidelity metric, which measures the similarity between embedding vectors encoded as quantum states. So this is an alternative to cosine similarity. So and this fidelity metric allows for efficient computation without the need to construct full quantum state vectors. And number three major contribution is integration with BART. So they have proposed a method to integrate with the BART language model. So BART gives contextual embedding, and now we have quantum embedding. The integration going to be holy. So uh, so basically they're not integrating with BART, but comparing the uh, BART based embedding and this quantum inspired projection head for embedding compression, and they're using some classical benchmarks for this. The performance is measured using the NDCG at 10 metric, which evaluates the ranking quality by considering both the relevance of results and their positions in the order list. So the results. This method achieves competitive performance relative to classic models while utilizing significantly fewer parameters. 32 times fewer. Well, remember that we are using qubits quantum circuits, so parameters should be fewer. The approach shows notable performance, particularly on smaller datasets, indicating its effectiveness in data scarce scenarios. Okay. The fidelity based metric is found to enhance the quality of sentence representations, improving benchmark performance compared to cosine similarity. So look at the technical details here. Quantum inspired compression, how are they doing this? So it involves mapping classical embedding to quantum states and applying quantum operations to compress the embedding. The use of single and 2 qubit gates allow for efficient dimensionality reduction. The compression head is designed to be integrated into neural networks, enabling end-to-end training with BART on classical hardware. Okay, and the fidelity matrix is used in a Siamese BART network architecture to train the model for semantic textual similarity tasks. This approach replaces cosine similarity with a fidelity-based measure, pushing the model to adapts its embedding representation to align with the fidelity measure. So the paper demonstrates the potential of quantum-inspired techniques in representation learning. The work highlights the utility of efficient low entanglement circuit simulations with neural networks as a powerful quantum-inspired technique. While the paper focuses future directions. While the paper focuses on NLP tasks, the method proposed are generic and could be adapted to other representation learning problems. Future work could explore the application of these techniques to different domains and further optimize the quantum-inspired projection head for improved performance and efficiency. Overall, the paper presents a significant contribution to the field of representation learning by introducing innovative quantum-inspired methods. So this figure 1, this one discusses various approaches to embedding compression. Like compression can happen after layer 2 or after layer n at the end of everything. So this is the Siamese twin BART. So sentence U, sentence B going through BART in both cases. Then mean CLS pooling, quantum inspired means CLS pooling. Then we arrive at embedding U, embedding B. The one of the twin measures quotient similarity UV, the other one does fidelity UV. So keyword is built by mapping a pooled embedding of BART to a quantum state in the Hilbert space. So given a pooled embedding U equals to U1 to UN, we have this mapping from R to the power n to H. Fidelity matrix also, here UB square, so UN up to UN and Bn up to Bn, so square, which equals U1 Bn dot U2 B2 dot up to UN Bn whole square. So this is classically tractable, meaning it can be computed using classical operations in classical computers because the quantum state is completely separable. So this is the figure for quantum inspired embedding compression of base BART. So this first part, sentence layer 1 up to layer n, then mean pooling, this is from classical BART. Then comes the encoding. Then we have this x1 up to x768 quantum bits, qubit representations. So only the red components are tunable. These are the red components, and here these are the U51 to U257s and such. Gain components correspond to the different encoding methods. Psi I writes back the measured probability distribution of the ith qubit, and Enc is a data encoding. This is the equation where Enc is once again defined, a mapping from R power n to Hilbert space. So they also did evolution study, and the interesting thing is that for both classical BART and for quantum inspired head, both of them have improved in their performance, while last layers of BART are allowed to be fine-tuned. Also, the quantum-inspired head showed a more pronounced performance decline when BART's layers were frozen, suggesting it may have lower representational power compared to the classical head when used alone. Now, the fidelity matrix results are interesting. Results showed that model trained with fidelity-based metric outperformed those trained with cosine similarity. The matrix proximity to the Manhattan distance suggests its suitability for higher dimensional data, helping to alleviate the curse of dimensionality. So the main advantages from this quantum setup are like 32 times fewer parameter efficiency, superior performance when trained from scratch with smaller datasets, and the similarity metric is a great thing. Efficient compression as well, so scalability and integration, and potential for broader application. So that's all I have. Feel free to ask any questions, and I will also do some follow up research on this. Thank you.